school? How was school today?
Hello.
Today looks like the internet is very unstable.
Hello. Yeah, my one also very unstable.
It's just disappearing today. We see what we can do.
Yeah, actually, teacher, I want to say thank you to you, teacher.
Say again.
I want to say thank you to you, teacher.
Where is your teacher now?
The last chapter today only started.
So fast, ah?
Yeah.
Oh, I thought I'm faster than him. Looks like he's faster than me.
No. He everything go very fast, lah, teacher. He doesn't explain that slowly or understandably. He just go through.
Okay.
No, teacher, I have to thank you, teacher.
Yeah, welcome. Yeah, welcome. But you have to put in the effort. As I say, I cannot.
No, thank you, because the videos helped me a lot. The last time video, the SEM3, it helped me a lot. Now I can understand better.
Yeah, but you must put in the effort. You thank you, no point if you don't put in the effort.
Yeah, I am putting, but I'm watching it slowly and understanding it.
You're supposed to be asking questions by now. We still got, I think, probably 3 weeks time we should finish everything already.
Oh, okay.
Then we can start revision, start past paper already. Okay, anything you want to ask? If not, let us just let you view some video before we start.
So the physics paper is on May 18.
Okay, May 18.
Jadwal just came out.
Okay, good. Thanks.
That's for semester 3. Semester 2 is June 13.
Semester 3, June 30 lah.
No, semester 3, May 18.
May
semester 2, June 13.
Oh, June 13. Wow, a lot of tests. Okay.
No, my ulangan, watcher.
Yeah, it's your revision now. It's up to you to make the effort. Okay, let's watch this video. Short one.
Theory come from? It started not as a crazy idea, but with a light bulb. In the early 1890s, the German Bureau of Standards asked Max Planck how to make light bulbs more efficient, so that they would give out the maximum light for the least electrical power. The first task Planck faced was to predict how much light a hot filament gives off. He knew that light consists of electromagnetic waves, with different colors of light carried by different frequency waves. The problem was to ensure that as much light as possible was given off by visible waves rather than ultraviolet or infrared. He tried to work out how much light of each color a hot object emits, but his predictions based on electromagnetic theory kept disagreeing with experiments. Instead, in what he later called an act of despair, he threw the existing theory out the window and worked backwards from experimental measurements. The data pointed him to a new rule of physics. Light waves carry energy only in packets, with high-frequency light consisting of large packets of energy and low-frequency light consisting of small packets of energy. The idea that light comes in packets, or quanta, may sound crazy, and it was at the time, but Einstein soon related it to a much more familiar problem: sharing. If you want to make a kid happy, give them a cookie. But if there are 2 kids and you only have 1 cookie, you'll only be able to cheer them up half as much. And if there are 4 or 8 or 1,600,000, you're not going to make them very happy at all if they have to share 1 cookie between them. In fact, if you have a room with infinitely many kids but not infinitely many cookies, if you share the cookies evenly, each kid will only get an infinitesimally small crumb, and none of them will be cheered up. And they'll still eat all your cookies. The difference between light waves and kids is that you can't actually have infinitely many kids in a room, but because light waves come in all sizes, you can have arbitrarily small light waves, so you can fit infinitely many into a room. And then the light waves would consume all your cookies. I mean, energy. In fact, all these infinitesimal waves together would have an infinite capacity to absorb energy, and they'd suck all the heat out of anything you put in the room, instantly freezing the tea in your cup, or the sun, or even a supernova. Luckily, the universe doesn't work that way, because, as Planck guessed, the tiny high-frequency waves can only carry away energy in huge packets. They're like fussy kids who'll only accept exactly 37 cookies or 162,000 cookies, no more and no less. Because they're so picky, the high-frequency waves lose out, and most of the energy is carried away in lower frequency packets that are willing to take an equal share. This common average energy that the packets carry is in fact what we mean by temperature. So a higher temperature just means higher average energy, and thus by Planck's rule, a higher frequency of light emitted. That's why as an object gets hotter, it glows, first infrared, then red, yellow, white, hotter and hotter towards blue, violet, ultraviolet, and so on. Specifically, Planck's quantum theory of fussy light tells us that light bulb filaments should be heated to a temperature of about 3,200 Kelvin to ensure that most of the energy is emitted as visible waves. Much hotter, and we'd start tanning from the ultraviolet light. Actually, quantum physics has been staring us in the face since long before light bulbs and tanning beds. Human beings have been gazing into fires for millennia, with the color of the flames spelling out quantum all along.
Okay. Hope it helped you. Right, let's start the class.
New chapter, right, sir?
Yes,
I already downloaded the worksheet.
Good. If you download the worksheet, you have to work on it. Start after learning it, do the question. That's how you force it in, and then also start revising all your second term work you have done two together.
Watch your videos also.
Okay. Under quantum physics, topic 24, you will start. Yep.
Sorry, teacher, I just want to say that means all the video, right, teacher? The one you posted.
It's on YouTube.
Hello? Yeah. So just watch it and understand it and then do exercise from it, right?
Yeah, watch it, understand it, and then solve the problem. I think your book is good enough. If you can solve it topic by topic or subtopic by subtopic, then after that do the focus one. I think you should be ready for exam.
Oh no, teacher, I very bored reading book. I prefer watching your videos, makes me understand.
No point buying too many books. Concentrate on one book. Your book is good enough.
No. I'm trying to say is your video, it doesn't make me bored, teacher, because I boring to read books. So your video explain better.
Good. You can introduce it to your friend. Especially those who don't do well, you can introduce them, ask them to go to YouTube. It's free of charge.
Yeah.
Okay. Anything else you want to take?
No, we can start, teacher, no problem.
Okay. So this one picture summarize for you what we are going to study in this topic. So we are going to divide into different subsection. 24.1 photon, 24.2 wave particle duality. Right? You can think of matter as behaving as a particle or behaving as wave. Atomic structure, right? Energy level, speed of atom, speed of electron in an atom. Right? Or we use hydrogen to derive the equation, hydrogen atom, X-rays. Then we go to nanoscience by subsection. Okay, I'm going to do slightly differently. 24.1, I will start with photon first. Page 212. That's your book that we are using. Okay, so you're supposed to try for today 24.1 and 24.2. Okay. Let's always go back to syllabus, right, to check how much is required by the exam board. Of course, sometimes it's not clear lah. Right? Then you have to go to past year paper. Do past year paper, then we can see how the examiner will interpret the syllabus. Describe the important observation in photoelectric experiment. Recognize the features of photoelectric effect that cannot be explained by wave theory, and explain this feature using the concept of quantization of energy. Use the equation, this one. So you will start with this one. Start with this equation first. Explain the meaning of work function and threshold frequency. Use Einstein equation for photoelectric effect. This is the equation. Explain the meaning of stopping potential and use that one there. Okay, so very brief your syllabus. Okay, let's just go roughly to history. In the 17th century, they already know all this equation, which is not required. You don't need to know this equation now. The intensity is proportional to frequency squared. Right, then of course, 1665, we have the Great Plate of London. So of course, like now, right, we have the pandemic, so that the Great Plate there. So it killed sorry, I can't see what is written there.
Teacher, I can hear two voices, teacher.
Two voices, why?
No, I can hear you talking and another voice talking. Just stop first. Can you even hear?
I cannot. I can only hear one voice only. Unless there's a cross line.
No, I can hear both voices of yours, teacher, like running from one background to another background.
Oh, okay. I'm not sure what is the problem.
They're still running. It's still running. Something is wrong.
Let me check whether...
You are talking about kinetic energy and potential energy.
Huh? How come?
Yeah, I think you better restart the recording, teacher. Better.
I just check and see whether anything is running or not. What is happening? Nothing here. Nothing here. Or did you switch on something? Nothing here.
Oh, no, sorry, my fault. My fault. Accidentally
I suspect you are the one who switched on.
Sorry. Oh, watching the video just now, maybe accidentally on it. I didn't notice. Yeah. Okay, you can continue, teacher. Sorry.
Okay. We have the Great Plate of London, 1665. Killed quite a lot of people, 75,000 to 100,000. So of course, that is the time where those who are staying in London will move out. To if they got country home, the richer people will stay in the country until the plate die off, so that they don't get killed also. So anyway, there's a good opportunity. That's where Newton started with his classical physics. So classical physics is from about 1650 to about early 1900. We call it Newtonian physics. So far, that's what we study so far. Where we deal with a small velocity compared to speed of light, and large distance, collision of car, moving of car, moving of a ball. And modern physics start in early 1900, right? Until now, right? You are here. This one we deal with large velocity, close to the speed of light, and small distance. Small distance means size of the atom lah. Speed of light, very close to that. Right? Small distance, 10 to the power minus 9, very small. So it means that for what we see, what we can deal with, we use classical physics. For the size of atom there, and near the speed of light, you have to use modern physics. Okay, this one you can get from internet. We are not going to study all this. Right? Let's just cancel off what we are not going to study. Oops. I think your book also has something like that. Right? Failure of classical physics, Planck's hypothesis, wave particle duality, photoelectricity, Boyle's theory, quantum number, hydrogen energy, hydrogen spectrum. Right? Certain phenomenon will be observations, cannot be explained by wave nature of electromagnetic radiation. Example, photoelectric emission, and there's photoelectric emission. You send electromagnetic waves onto the metal surface, electrons are emitted. That's what we are going to study first. And then you cannot explain why electrons occupy energy level. Means as we move from one energy level to another level, electromagnetic radiation is given out. The name quantum physics was coined by Max Planck, derived from the observation that some physical quantities can be changed by discrete amount, or we call it quanta, as multiple of Planck's constant, rather than being capable of varying continuously or by any arbitrary amount. So we are more interested in discrete amount, small amount, discrete amount, not like continuous that we can heat a water to different temperature and given different amount of energy. Okay, so we start with energy of photon. Page 217. Detecting charged particle, we use a Geiger-Mahler counter. There's the detector. There's a counter. That can be the loudspeaker. Geiger-Mahler counter can be used to detect both alpha and beta particles, radiation. We can either use loudspeaker. You can use loudspeaker. You can connect directly to loudspeaker where we can hear the sound when there's a particle enter the detector. You can hear a sound crack, crack, crack. Then we know, right? We detect radioactive particle. Or use a counter. That is a counter where you just count the number of particles that's entering the detector. Right? That's a Geiger-Mahler tube. That can be used to detect the particle. That can be used to detect gamma ray. So gamma ray are electromagnetic radiation. There is waves. So it means that gamma ray can behave as particle. Okay, photon, particulate nature of electromagnetic radiation. Now you represent it as that. Just something, you know how you call that, right? Like a wave, not of the same amplitude, right? Just short form, that's what we call a photon. It has a wavelength. Photon, that one is for you to remember. Packet or quantum of energy of electromagnetic radiation. Energy of electromagnetic radiation is confined to small individual packet of photon, each of energy. That's the energy of packet of photon. F is the frequency. H is Planck's constant, 6.63 times 10 to the power minus 34, given in your value of constant. Right? And usually we will be using this one now. Instead of F, we replace it with we use C equals F lambda. We use this equation. Right? Value of constant. Have nowhere to find your constant. That's your Planck constant. Right? Magnitude of charge or electron volt is also the same value, except we call this one joule. Right? Electron volt is not given, so you just have to use the same value as electronic charge. And then speed of light in free space. These are things that we will be using very common in this topic. Okay, calculate for me using this formula number 1 in your worksheet.
Okay, sir. Sure.
Number 1 in your worksheet. Red light has a
Okay.
wavelength of 700 nanometer. Calculate the energy in electron volt of a photon of red light. Just using this equation as well. Just getting you to play with the formula to get to this equation. Okay, calculate that. Can?
Yeah, sir. Just give me 1 minute. I'm almost done.
Okay.
Uh, 1.78 times 10 to the power of negative 38 EV.
How do you get one? How do you get so high? You should get this value.
Oh, yeah, no, I got that. Then I divided with the 1.60 times 10 to the power negative 19.
Then 1 electron volt equals that. After that, you have to divide to get electron volt. So what you get 1.78 only, huh?
Yeah, I got 1.78 lah.
Okay, you got 1.78, good. Usually it's about that.
Sure, but my calculator showed differently.
Huh? So what? I think you pressed wrongly.
No, I got the I think I pressed wrongly,
You
but
get
the calculation
178
showed I
correct,
did
but
it like that also.
the power is all wrong. I think you did not change the sign. The
power
negative
wrong
sign. The power, you have got it wrongly. Okay, good. As long as you can get the number, make sure you're not so careless. Okay.
I never put bracket just now. Now I got the answer.
Okay, good. And let's just watch some video so that you can see what is happening.
Good grammar and spelling are important, but if you want to write essays that inspire, messages that forge brighter connections.
Can see now?
One of the big ideas in physics is that light can behave as waves or particles, and this demonstration of the photoelectric effect is a really great way of introducing that idea. What I've got here is a zinc plate, and if you want the demonstration to work, it's absolutely essential to give it a good scrub on both sides.
If you cannot see, let me know.
With a bit of iron wool, and that just removes the surface oxide layer. I then place the plate on top of this gold leaf electroscope. I've also got an ordinary desk lamp and a UV lamp. Now, in order for the demonstration to work, this plate has to be negatively charged, and I can do that using the method of charging by induction.
Right, it's checking by using the charge there. Show you how the electroscope.
Now, let me say that again.
Stop a bit.
I've got a perspex rod here, which I can make positively charged by rubbing with this bit of cloth. I bring the rod close to the plate, touch the plate with my finger, remove my finger, then remove the rod. Now watch what happens when I shine visible light onto the plate. Absolutely nothing. That's actually a really important part of the demonstration. Your students need to notice that with visible light, nothing happens. But watch what happens when I shine ultraviolet light. You can see that the gold leaf immediately starts to fall. And that must mean that the UV light is somehow discharging the electroscope. We know that we started with negative charge on the plate, so the UV light must somehow be releasing the electrons. And the important thing to notice is that it's the frequency of the light that makes a difference. Remember, with a visible light, it doesn't matter how bright it is or how long it shines for, it doesn't release any electrons. Now, this phenomenon cannot be explained using a wave model of light, but we can understand it if we adopt the idea that radiation arrives at the plate as packets of energy, which we can call quanta or photons. A single photon of UV light can release a single electron from the plate. However, a single photon of visible light has less energy and so cannot release an electron. Now, this is a relatively simple demonstration to do, but it took the genius of Albert Einstein to explain what was going on. And it was for that work that he was awarded the 1921 Nobel Prize, not his work on relativity.
Okay, let us finish our topic.
Are you going to divide this into 2 videos, sir?
No, because it will disturb the video.
Can continue then, sir. Yeah.
Because it's all
I
complete.
can pause later in YouTube.
It's quite a long. We probably have to carry on tomorrow also. Okay, photoelectricity. Page 212. Let's just review what we have just observed. Experiment demonstration of photoelectric effect. There's your zinc plate. That's your radiation. This your whole thing is that gold. This is your gold leaf. So the whole thing is called your electroscope to detect the presence of charge. Okay, electroscope. You clean your zinc plate. Right? Clean the zinc plate and place it on top of your disc of the electroscope. And then you charge the electroscope negatively. Then you use ultraviolet light, right? Radiation from ultraviolet, falls on the zinc plate, and you observe the diffraction will go down. Then decreases the electrons are emitted. Now, of course, we can place it this way. It doesn't have to be on top of that. Can be placed next to the zinc plate. Doesn't matter. Diffraction of the leaf is unaffected. We can do the experiment. Gold leaf electroscope is charged positive. We charge it positive. A clean zinc plate is placed on the cap of the electroscope. Just now we charge it negative. Now we charge it positive. The zinc plate is exposed to ultraviolet ray from the mercury vapor lamp. Same as before. We use ultraviolet light. But now we charge positively. That's all. When we observe the diffraction of the leaf is unaffected. Can you explain why? Ken, any idea?
Because it has positive charges around it, sir.
Yeah, there must be a reason why it doesn't go down. If we put negative charge, it will go down. But we put positive charge, it won't go down. So what does it tell us?
That means with the presence of positive charges, it will never go down. So it's unaffected. That's what it's trying to tell.
Yeah, why? Why? There must be some way to explain it. Why this is happening? Never mind. If you can, you explain. If not, we will wait for it. Okay. We charge it negatively. Charge a zinc plate negative. Charge the electroscope negatively. Put a zinc plate there. Can be horizontal, can be vertical. Doesn't matter. Then we shine ultraviolet light. Okay, we can use laser. Can use visible light. Laser and visible light. We can see no effect. ultraviolet light, we see that the deflection goes down. Right? The leaf falls gradually, the fall is stopped. Right? For this case of ultraviolet, the leaf stops if a glass plate is placed between the lamp and the zinc plate. Right? So if the ultraviolet source, if we put a glass plate between ultraviolet source and a zinc plate, then the leaf will stop going down. Right? Simple reason is because the glass plate will absorb the ultraviolet light. So it's the ultraviolet light that causes the diffraction to go down. Right? We can shine different light source and electromagnetic radiation, laser, visible light, ultraviolet. So what is the explanation for the first part? Where you charge positively, electrons emitted are attracted back to the positive charge plate. It's still happening. When ultraviolet falls on the zinc plate, electron is still emitted. But now remember, the plate is charged positive. So the plate will attract back the electron. So there is no chance for electron to be for the positive plate, for the positive to be discharged. Right? No source of electron to receive, so that the deflection will go down. Electron emitted is attracted back. So that's why it doesn't go down. But if we charge negatively and we shine ultraviolet radiation, we observe that it's going down, because ultraviolet radiation causes electrons to be emitted or ejected from the surface of the zinc plate. So as more and more electron is emitted, the diffraction will go down until finally zero. All the electrons are emitted completely. Okay, remember your electromagnetic spectrum. You can remember that order: 19, then 16, then 10 to the power 14, 10 to the power 11, 10 to the power 9. That's the simplest way. So what is the what? See whether you can remember what is this region? The leftmost. Yep. What's the leftmost? What is it? Gamma ray, ultraviolet, visible, radio wave, microwave. What is it? Can you remember or not?
Cannot, I forgot already.
All this must be in your head. Okay, we start with gamma, X-ray. Then after that, ultraviolet. Right? Visible is very small region.
Infrared.
Visible is very small region there. That small region is visible. And infrared. How about this one? Right? Microwave. Then radio wave. Right? 10 to the power 9 Hertz. Radio wave. Micro is 10 to the power 11. You need to know. You need to know all this region. That is the best, the simplest way. 10 to the power 19, start with 19, 10 to the power 16. Right?
Slowly decreasing.
About 10 to the power 3, then 10 to the power 2, 10 to the power 3, 10 to the power 2.
10 to the power 2.
1,000, 100, 1,000, 100. How do you remember it? Right? So if we have a minimum frequency here, then it must be maximum wavelength. This is important. Right? Minimum frequency, maximum wavelength. Right? You want a more detail, you can use this one. Okay, but as I said, this one is good enough. If you can remember this one, good enough already. Can work out the wavelength. Right? Effect of different electromagnetic radiation on different metal. Right? We can shine electromagnetic radiation on different metal. We can use zinc, can use sodium, can use cesium. Is illuminated by electromagnetic waves of different frequency. This is my symbol for electromagnetic radiation, EMR. Okay, so if we use zinc, X-ray, remember, high frequency, this one is low frequency, right? E equals HF if you like. High frequency, more energy. Okay, for zinc, X-ray can, ultraviolet can, visible cannot, infrared cannot, radio cannot. Sodium, X-ray can, ultraviolet can, visible, yes, except orange and red. Orange and red are longer wavelength, so smaller frequency. Infrared cannot, radio cannot. Cesium, X-ray only, right? Ultraviolet cannot. Remember, longer wavelength to the right hand side, higher frequency to the left hand side.
Sure.
Yeah.
So I missed the orange and the red.
Doesn't cause emission.
Only that one cannot.
Okay. The blue can, the green can. Okay.
Okay.
Not all from the visible region. Usually visible region doesn't cause emission. Only for sodium, a small part of the visible spectrum.
Okay.
Okay, which has a longer wavelength, red or blue?
Which has longer wavelength, red or blue? Red, teacher.
Okay, good. Red has a longer wavelength. Photoelectric emission to occur, the radiation must be, that's our conclusion. The radiation must be greater than a certain minimum frequency. Right? Just like what we have seen here. There must be a minimum frequency here. All this frequency, higher frequency can, minimum frequency, lower than that frequency, no emission, same as here. Right? Minimum frequency somewhere here. All this higher frequency, yes. Lower frequency, no. Must be greater than a certain minimum frequency for emission to occur, or another way to express it, less than a certain maximum wavelength. Okay, let's look at the laws of photoelectric emission. These are what I call experimental observations. We call it laws. Okay, let's look at the parameters. This is your incident photon. Right? We don't think it as waves anymore. We think of this wiggly sign there, more packet, more waveform there with different amplitude, that's all. Right? Photons of electromagnetic radiation, we think of it as particle. So there will be number of photons, NP, intensity. We define later on. And then frequency for the incoming photon, number of photon or intensity and frequency. Then we are interested in the electron that's emitted, number of electrons emitted per second. And we are interested in the maximum velocity. Okay, let's state the observation. I hope this will help you. You can think of risk. Instead of risk, you can think of it as, instead of the S, you can change the S to the T. That will help you to remember. Can remember what R? Rate of emission.
Rate of emission.
And the next one is intensity. Instantaneous emission. And T is threshold frequency. Then K has to do with kinetic energy. So about what is, can you state for me about rate of emission? It's rate of emission of electron. Yep. What about rate of emission? This one you have to remember all of them. Yep, Ken?
Actually, I can't explain right now because I'm also looking at the book for the answer.
I'm hoping you can remember what your teacher teach you. Then if you can repeat it, then you force it in again. No? But if you cannot remember, it's all right.
Teacher, he doesn't even teach that much properly. He like go through and then this one. I mean he takes his long time, but the class like boring teacher, like can't even like understand things sometimes.
No wonder all of you
students
didn't do that
like
well. A lot of you didn't do that well lah. Only got those good students can do well.
Those really study well without the teacher help, yeah, they did well.
Yeah, those who are good students know how to study one can do well lah. Okay, it's okay. Rate of emission of electron depend on intensity. Right? Number of electron emitted per second depend on intensity. Instantaneous emission of electron when metal is illuminated. As soon as you shine the electromagnetic radiation on the metal surface, electron is emitted. Doesn't have to wait. Or some people call it, there's no time lag. And threshold frequency. There's a threshold frequency, we call it F0, below which no emission will occur. My way to explain for emission, the frequency must be greater or equal to the threshold frequency. And kinetic energy, maximum kinetic energy depend on frequency of the electromagnetic radiation. Maximum electron kinetic energy does not depend on intensity. Right? Maximum kinetic energy depends on frequency, doesn't depend on intensity. That's my way of writing. Maximum velocity depend on frequency, independent of intensity. That means you can shine your light as bright as possible. If it doesn't emit, it won't emit. That's what it means. Anything you want to ask?
1 minute.
Pay you to memorize it.
Instantaneous emission is what again? I don't understand.
Instantaneous means as soon as you shine electromagnetic radiation on the metal, the electron is emitted. You don't have to wait.
What is emitted?
Not like classical physics, where you put a metal on a flame, and then it take a while for the metal to heat up, and then finally the heat to travel to your finger, and then you feel hot, and then you release the metal. Right? You don't have to do that. As soon as you shine the electromagnetic radiation onto the metal surface, the electron is emitted or ejected.
Oh, like immediately the electron is
very fast, straight away. Instantaneous means straight away.
Oh, okay.
Not like you have to boil water, you have to wait for it. Right? It takes a long time to heat it up. Right? It takes time for it to receive heat and then finally boil. No need. Right? It's like
so threshold frequency means
it's a minimum frequency of electromagnetic radiation that you need to use. If the electromagnetic radiation is less than this minimum frequency, it cannot cause emission of electron in the metal.
That's what is meant by threshold frequency. That means no emission
at
all.
Meant by threshold frequency. Anything else you want to ask?
Okay, not dependent. So how come this one is dependent on frequency electromagnetic equation but not dependent on intensity?
These are observation, right? Observation. Okay. Then after that, we try to use classical physics to explain, and then we find the problem with classical physics. Then we come out with new theory called quantum physics to explain. No? So now I'm just giving you the observation. After that, I will go into how we explain that. Okay.
Okay.
Okay. Both particle and wave and particle, both interference and diffraction are properties of waves. Photoelectric effect and production of X-ray show the particle nature or particulate nature of electromagnetic radiation. And this one you need to remember. The picture will help you. electromagnetic radiation coming in, electron emitted. So photoelectric effect is the emission of electron from the metal surface, when illuminated by electromagnetic radiation of certain frequency, not all frequency, only certain energy or certain frequency. Right? That's why we introduce the idea of threshold frequency. Right? So we can use the word irradiated or illuminated. That means we shine the electromagnetic radiation on the metal surface. Okay? Any comment?
Okay.
Memorable only this one. The key is metal
okay.
surface, electromagnetic radiation of certain energy. Not all energy, certain energy or certain frequency.
Okay.
And we are just summarizing the experiment, that's all. What is photoelectric effect?
So emission of electron means is coming out, is it?
Electron is coming out of the metal surface.
Oh, okay. When illuminated meaning, that means coming out, that's the meaning, right?
Illuminated means we shine the electromagnetic radiation on the surface.
You mean the electromagnetic thing on the surface of
just
the
now
metal
the experiment
shine.
You shine ultraviolet lamp onto the zinc plate.
Metal.
Just now the experiment. That's called illuminator. You don't want to use.
Oh, you mean shining the thing? Okay.
You just use shine. No? When you shine electromagnetic radiation on the metal surface.
Okay, can continue, sir.
Okay. Let's look at conductors and metal. We have done that in the second term, where your positive ions are vibrating. You have free electron or delocalized electron. These are electrons that can move. These are your positive ions. All conductors have free, or we call it delocalized electron. These electrons are not tightly bound. They can move within the surface like air moving in the room, but they cannot leave the surface. They are bound to the negative ions. They are free to move within the metal. Right? But remember, there's a resultant force on the free electron that prevent them from escaping. As the electron moves towards the surface, is retarded by resultant attractive force. Right? Remember, the electron is surrounded by a lot of positive ions, whether nearby or far away from the neighboring positive ions. The electrons so if there is a resultant pull inwards, resultant force pulling inward, the electron must slow to a stop before reaching the surface. So it cannot escape at all, the electron. An electron in the metal does not have sufficient kinetic energy to escape. Right? So as long as you don't give kinetic energy, the kinetic energy of the electron inside the metal surface is not sufficient for it to escape. To escape, the electron need minimum energy, or we call work function, from the external source. Right? That's why we have thermal emission. We heat the metal to give electron out. Or we use electromagnetic radiation to emit the electron. Okay, so this picture just to explain to you. Right? There's a free electron trying to escape. There's a surrounding positive ion. Right? Just showing a few, that's all. Right? So there's attractive force. Bring it inwards, going sideways, pulling it sideways, and also pulling it down. Remember, these are only a few. So of course, there are other pull, 3 dimensions, can imagine 3. So that will be a resultant force. That is your resultant force. This resultant force will slow it down. So there's no chance for it to escape. So work function, this one also for you to memorize. Minimum energy of photon or minimum energy of electromagnetic radiation to cause emission of electron from the surface of metal. T is metal surface, minimum energy of electromagnetic radiation of photon. It escape with 0 kinetic energy. Okay, so the photon has energy E equals hf. So work function, that's a symbol for work function. Either we can use phi or W. So W equals to hf naught. F naught is the threshold frequency or the minimum frequency of electromagnetic radiation for electron to be emitted from the surface of matter. Okay, any comments so far?
Fair answer.
That you digest.
Okay, so that means basically it means that electron is trying to escape in the first place by the positive ion, but it has no choice, is attracted because negative and positive. So the resultant force by the electrons makes it stop, is it, the electrons?
You don't need to go too far that way. You just need to remember that it cannot escape at all, but it needs a minimum energy we call work function for it to escape from the metal surface. That is called the work function.
Sorry, need minimum energy to what, teacher?
Minimum energy. Yeah, minimum energy to escape. So that minimum energy is provided by the electromagnetic radiation or photon.
Okay.
That's why it's written here. Minimum energy of photon or minimum energy of electromagnetic radiation to cause emission of electron from the surface of metal with zero kinetic energy. Right? Electron emitted, but as it leaves the surface, it leaves with zero kinetic energy. That is what I mean by work function.
Oh, it has to be zero, but then kinetic energy isn't it moving very fast? That means in this case it's moving very slow, is it?
Zero velocity. That's what we want. That is what I call work function. That means the electromagnetic direction has the same value as the work function. Then the electron will emit at with zero velocity. That's all.
Okay.
I'm just trying to help you to see that there must be a minimum energy because there is a resultant attractive force, but you don't need to know all this. Just remember what is work function, what is threshold frequency. Memorize that.
Okay.
Okay. 19, there's the question 2, work function, 1.9 electron volt for cesium. For beryllium is 3.9 electron volt. Okay, calculate for 1.9 electron volt to Joe. Give me your value. Change 1.9 electron volt to Joe. Your question 2 in your worksheet.
Yeah, I got it. What is the work function? 1 minute. Okay.
Your answer should be 10 to the power minus 19 something there. If not, means you're done wrongly.
Fair answer. Work function mine equals to W over H. W equals to HF9. Just a minute.
Just know how to convert, that's all. 1 electron volt is how many joule? Yeah, what's your answer?
So the formula is W equals to HF minute, but then the F minute you substitute one inside.
No formula lah, Srini. This is a simple conversion of electron volt to joule, that's all. That's all you need to know. 1 electron volt is 1.6 times 10 to the power minus 19 joule.
So times 1.9.
To get you to do your conversion, straightforward conversion from unit to unit, electron volt to joule. That's all.
Oh.
So you must remember the value, same as the charge. Yeah, what do you get? Just multiply only 1.9 times 1.6. That's all.
I got 3.04 times 10 to the power negative 19.
3.04 times 10 to the power minus 19 joule. Okay, good. That's what you should get.
So then why they show the answer that 3.9 EV for?
3.9 is for beryllium. I didn't say that's the answer. I'm just asking you.
Oh, sorry. Oh, I thought that was the answer. Okay, yes, got it.
Okay, another way of thinking of it, you can think of it as potential well. Right? This is a different way of helping you to understand what is work function. That's all. Okay. Compare electron with a person. Right? If the person want to jump up, he must have enough. As long as he reach the top there, then we say escape with it. Right? So the person, so compare electron with a, right? This is your potential well. Right? Person, compare electron with a person in the bottom of the well. That's your person, or that can be your electron. Totally smooth side. The side is totally smooth. Right? So you cannot climb. You have to jump up. The person can only get out of the well by one jump only. Right? No jump and then jump again. They cannot jump halfway up and then jump again. No, only one jump to escape. Okay, so it means that it must have that amount of energy, the green one, that amount of energy to escape. Right? So that is your potential.
Then the blue one, sir?
Wait. We are very patient.
Okay.
Electron at the bottom, our potential well must be given enough energy to escape in one jump. Right? Same idea. So that energy is provided by this high energy ultraviolet radiation. Right? That energy is the blue one. It's called the quantum energy. Right? This energy is the work function for the material. That energy, work function, the green one. Okay, so you just give that amount of electromagnetic radiation equals to work function, then you just escape with zero velocity. But if you use high energy ultraviolet light or quantum, the photon has greater energy than the work function, represented by the blue line energy. Right? High energy, violet, quantum. So that's your quantum of energy, the blue one. Electron will leave the metal with this amount of energy. Right? So that is your kinetic energy. Okay, so that's called your maximum kinetic energy. Okay? The green one is your work function. That's the metal, the metal, the work function. So you must have this minimum energy provided by this radiation or this photon of electromagnetic radiation before it can escape with maximum kinetic energy. Okay, so Einstein summarized this called Einstein's photoelectric equation. EK max equals to HF minus phi or W lah. Right? So all this picture is just trying to help you understand the formula, that's all. Right? Same idea. Right? That's your energy well. That's your electron. To escape, you must have that work function, that minimum energy. So these are what we call trapped electron, trapped in the potential well or in the metal. That is your work function. When a photon meets an electron, the photon gives all the energy to an electron. So if the photon comes, it meets an electron, it will give all its energy. Right? So we can summarize. Of course, we provided the photon energy is enough, right? Greater than the work function. If not, the electron will not accept the energy. So basically, it's a conservation of energy. That's all. The equation. Conservation energy, photon energy equals to maximum kinetic energy of emitted electron plus work function. That's all. So electron emitted with maximum kinetic energy. Okay, so that's why it means instantaneous emission. As soon as you shine, the electron is emitted. That's all. That's the equation. As long as you satisfy this equation, as long as your HF is greater than your work function, you will escape. Right? That's why we explain instantaneous emission. Right? So that is your symbol for maximum kinetic energy of emitted electron. There's your energy of incident photon. That's your work function. We can call it W if you want to. Sometimes I use phi, sometimes I use W. So when a photon or energy E, that's your photon energy E, equal to that work function or greater than the work function, falls on the surface of metal, is observed, part of the energy of the photon is supplied to work function. So part of this energy goes to this work function, part goes to the kinetic energy of the emitted electron. Right? The work function of the electron, and the rest appear as maximum kinetic energy of the emitted electron. So that explains why we have electron emitted at maximum kinetic energy. And that also explains why the kinetic energy depends on frequency. Greater frequency, greater kinetic energy. Okay. Anything not clear?
Okay, so basically means without the HF, they won't get like the part of the energy, and then that's why I mean
work function
it is the maximum
is the minimum
dependent
energy. Work function is the minimum energy. I understand the equation. That energy is provided by the electromagnetic radiation. So the electromagnetic radiation must have energy equal to work function or greater than the work function before the electron can escape with kinetic energy. If it's equal to work function, then the kinetic energy is zero. That's how we define our work function.
So if the work function is more, then the maximum kinetic energy will be more also lah. Right.
Work function is constant for metal. So what is deciding is the electromagnetic radiation, energy of electromagnetic radiation. It must be equal or greater. That's all. For electron to be emitted.
Okay.
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 Right? Basically, we are just using conservation energy. Okay, so that's how we define our work function equals to energy of the photon, where the electron is emitted with zero kinetic energy. Right? Now we can use analogy to help us understand what is happening. To visualize what is happening to electron in the metal, think of a big hall. Right? The hall represents the metal. Student running at random in the hall. Right? That represents the free electrons moving about in the metal. And photons. Right? You can think of photons coming in on the metal, right? Hitting the metal surface as like students standing on front of the stage and throwing balls, or better to think of it as packet of water at random, right? Not aiming, just at random. So not all the balls will hit the student. Right? Imagine that the ball, if the packet of water fall on the floor, it doesn't break, right? But if the packet or ball hits the student, it will wet the student. That means it's given the energy to the student. That will cause emission. We call that emission. Okay, let's look at Einstein's photoelectric equation. That equation. Not all photons would meet electron, as both are relatively small. Remember, electron and photon Photons are just packet of energy. They are both very small. So not all the photons will be an electron. So it will not all the photons will cause emission. When a photon collides with an electron, it transfers all its energy to the electron. You cannot say, I give you a little bit, I take a little bit. No, the photon will just disappear, give the energy to the electron. Transfer energy is instantaneous. That means straight away. Huh? Just I ask you, you want money? You want money, you take it. Straight away. No need to say, I don't want, I got enough money, no need to do that. You straight away, you take it or you don't, you leave it. Huh? That's why it's happening. Transfer energy is instantaneous. The photon gives all its energy to the electron and disappear. Okay? That's what it means by instantaneous emission. The electron straight away receive the energy and then it escapes. Anything not clear?
So basically, that means the photon will give all its energy to the electron. That's it. Even though both are small. That's it.
As long as the energy is greater than the work function, the energy is given to the electron will escape.
Wait, what do you mean by energy greater than work function?
Yeah, that's the equation we have been telling you. The electromagnetic direction energy must be greater than the work function. If not, you don't have kinetic energy at all. It cannot be negative.
Okay, understood, teacher. Can go to the next slide. Teacher, how many hours the class are? 1.5 or 1 hour?
1 hour only. I'm trying to finish it soon.
Oh no, already exceeded already. That's why.
I know. I want to cover enough. Can't leave you halfway and then teach you another halfway. Right?
Okay.
Cover enough first. If the energy of the photon is not enough, the electron will not receive it. Right? That's what it means by where you got negative kinetic energy. Unlikely the electron will receive 2 photons to escape. That means it cannot receive 1 photon, less energy, and then another photon, less energy, another energy, and escape. No such thing. Right? No. The energy must be enough for it to escape straight away, not receive 1 photon and then another photon. Unlikely, because both are very small. Where the energy is just sufficient to escape, then the electron will leave with 0 kinetic energy, or work function equals to hf0. F0 is the threshold frequency. For electron to escape, the photon must have energy equal or greater than the work function. Add energy must be equal to the work function or greater than the work function. No such thing as less. Then there's no escape. When the energy of photon is greater than the work function of the metal, the electron is emitted with maximum kinetic energy. Okay, as long as that energy is greater than the work function, then the electron escape with maximum kinetic energy. So that explains to you why we need a threshold frequency. Okay. Anything that is not clear?
Just give me 1 minute, teacher.
Okay.
Oh, okay. So that means less photon means the electron cannot escape. That means like maybe a little bit will escape, but if it like you only have like sufficient energy, means that's why you'll escape with 0. What is that? 0 kinetic
if the photon got energy similar to work function, then it will just escape with 0 velocity. If the photon energy,
if it has like quite a lot, then it'll be maximum.
Then it will appear as maximum kinetic energy. The rest.
Oh, where FO is the threshold. That means threshold frequency means no emission lah. That's the meaning.
No, it's emitted, but with 0 kinetic energy or 0 velocity.
Oh, okay.
Okay, there from the equation, these two the same. Yeah. Then this is 0 kinetic energy. If this is less, no emission. Negative kinetic energy means no emission.
When the energy of photon is greater than the work function of the metal. Okay, understood, teacher. Yeah, I understand this.
Okay, usually we show photon as bigly signed, not as waveform. Photon entering the metal may not encounter any electron. It just pass through. it may encounter electron. Then of course you don't go and ask, can you accept the energy or cannot accept energy? Right? If the energy is not sufficient, the photon will just pass through. The electron will not accept it. No emission, no? Photon coming in can escape. So if sufficient energy, the photon give all its energy to electron, and the photon disappear, the electron escape. Right? Electron emission. More photon, right? Remember, one photon emit one electron. So more photon incident on the metal surface, more likelihood of electron and more electron escape. That's why the rate of emission depends on intensity. Right? More photon means the intensity increase, so more electron will escape.
So less photon, lesser chance of the electron escaping, so therefore lower rate of emission lah. So,
less photon means less electron emitted.
Yeah, and the rate of emission is low lah, way more lower.
Okay with that?
Yeah, okay. I can continue.
Okay, so if we draw the remember the current, the electron is detected as a current. The intensity is a photon hitting the surface with the particular energy. Okay, so we can write the equation. Well, it should be proportional. The current that we detect is proportional to intensity, where K is usually less than 1. And K is the gradient of the graph. What does it mean if K is 1? Yeah, what does it mean if K equals to 1? Right? Remember, your current is number of electron, charge of electron divided by T. What does it mean when
K equals to 1 means the amount of current is equal to the amount of intensity lah. So
it means that every photon will cause an emission, which is unlikely. Right?
Yeah, that means it's a perfect one lah. That means which means it's impossible.
Each photon meets an electron and cause emission, but it's unlikely. We won't see such case because both are very small. Right? Why is K less than unity? Right? Not all electron will cause emission. Okay, some photon will miss the electron, will not meet an electron, so it just pass through.
Oh yeah, common sense. Yeah, okay, correct, teacher.
Okay, let's look at the equation, then we will probably call it a day. Kinetic energy frequency graph, we are looking at the equation. Okay, we plot our maximum kinetic electron when photon with different frequency falls on the metal surface. Right? We use electromagnetic radiation of different frequency, and we measure the maximum kinetic energy. Yeah, we use the same metal. So how does the graph look like? How does the graph look like? Is it a curve? Is it a straight line? Is a straight line passing origin? Or is a straight line got positive intercept? Look at the equation and tell me. We are looking at the equation. We are plotting.
What's the question again, Chair? Sorry.
I'm drawing the graph. What type of graph is it?
Okay.
I'm drawing this graph. EK max against frequency. What type of graph is it?
Directly proportional.
Okay, be directly proportional. This show you there is a negative y-intercept. The h and phi are constant. Written for you everything.
Oh, that means it's going down. It's going down. It's going down.
So you should be able to read the equation. Compare equation of straight line.
It's going down.
Yeah, there's the graph there. Negative intercept. So what does the gradient represent?
Gradient represent the h lah.
Okay, what does y-intercept represent?
The maximum kinetic energy.
Don't simply guess lah. Look at the equation. Learn to understand from the equation.
Yeah lah, you literally just showed me EK max.
Where got? I'm asking you this negative intercept lah. This one is the C
yeah,
lah. C.
Okay, the C, that one, the very weird symbol, what they call it, or something, that one lah. Yeah,
What
the
that one
negative,
lah?
that one.
You must know what does the symbol stand for.
I don't know what the symbol stand for.
You are not paying attention in class. It's a work function. Gradient is your Planck constant H. Look at the equation and compare, that's all. Y-intercept is that's your y-intercept. Work function. So how about the x-intercept here? This one. X-intercept, put your kinetic energy equals to 0, y equals to 0. So what do you get?
Frequency.
Threshold frequency, not just frequency. Right? Y equals to 0, this equals to 0. X-intercept is the threshold frequency. This is your F0. Okay? Anything not clear? Remember, we are looking at the equation now. Concentrate on the equation and compare the equation of straight line. And then we know it's the equation of straight line with negative y-intercept. Anything that's not clear before I ask you some question?
So far,
okay. Right, same question. Sketch a graph for the metal of higher work function. Now I'm using the same experiment. I'm using a metal of higher work function. Which is the answer?
where answer metal or higher work function.
Just using this equation, that's all. I'm using a higher work function. So what is the answer?
Function. Can you go back again, Ch?
You should have your book in front of you and refer to your book. Yeah, what's the answer? A, B, C, D. Just applying this equation, that's all.
Okay, go back to the answer, Ch. I want to tell the answer. The answer is B, teacher.
What answer?
B.
B. How do you get B?
Yeah.
How do you get B? Not simply tembak. You don't simply aim and get the answer. You reason it out. Greater work function.
Okay. Yeah, the one which is not a line one, the intersection point is
you don't understand.
It's a negative work function.
The gradient doesn't change. We change the work function. So we make this one more negative, that's all. The straight line is still the same. Same gradient. More negative, that's all. So the answer should be donkey. Yeah?
Hey, why donkey, Ch?
On the graph, sketch the graph of EK max against frequency where the metal of higher work function. Higher work function means more negative, this one. That's all. Right? Gradient is constant. So it's parallel. The two lines must be parallel. Greater work function means more greater threshold frequency. That's all. Yeah. Any comment? Anything still not clear?
Clear, teacher.
Okay. So tonight your homework is 24.1 and 24.2. We will stop here. No point in going any further. You have to digest what I teach you. You better review it tonight so that you can follow tomorrow. We are going to use the same thing. Right? We cannot finish today. So we are still going to use this equation. So we have to learn to understand that equation. And then we are going to look at why the wave theory is insufficient to explain photoelectric emission. Okay. Anything that you want to ask? If not, I will stop here for today.
No.
Any comment? Anything you want to ask?
So far, no.
Okay. If not, we will call it a day.
Okay, thank you.
See you tomorrow, same time.
Yeah,
Okay.
same time.
Okay, I'll stop here.
Thank you.